Can you hear me? Yeah, okay.
All right, everybody, we're going to get started with the second morning session. This session, we have two invited talks. And to start it off, we have Nicola Iro, who will be speaking about circulation regimes of extrasolar planets. So take it away.
Thank you. So I just take 1 second of my time as a co-organizer to ask all the speakers if they're willing to send their presentation file on the Slack channel. It would be very nice for everyone. We had a lot of nice contributed talks, and we will have some more. I am sure. So yes, thank you for that. It was not so easy to make this presentation because we already talk quite a lot about clouds and circulation, and I know we will have some also upcoming talk about that too. So I tried to give you an idea, not so much on what are like a very big question answered by such method, but more like what the question I was asking myself when I wanted to approach clouds in for my GCM. So if you have a GCM and would like to implement clouds, how you would do that. So as a brief introduction, I will talk about the effect of clouds on circulation and the effect of circulation on clouds, and then a few ways to implement clouds in models. So Vicky already talked about that, and a few others too. So it's really not easy to see what will exactly be the net effect on the radiation from clouds, because on one hand the cloud coverage would make more reflection from the sunlight, so it will cool the atmosphere, but on the second hand more cloud particle would increase the greenhouse effect. So I just wanted to make a very simple exercise, the simplest radiation budget you can get. So if you make the balance between internal reflected and transmitted at the top of the cloud, in the atmosphere and on the ground, you can easily get to this relation here when you put everything to equilibrium. And that's really depend on the reflective effect, the transmission, and the absorption of the clouds. So let's put that on a clear sky. So obviously, no cloud. So you put the atmospheric scattering and absorption here values. So you see that with this low value, you get 283K. If then you put volcanic aerosols there, so you increase a little bit reflection and transmission and absorption. Just a little bit each time, but and you have a cooling effect. If instead you put water cloud, then you increase quite substantially the absorption. So of course it's like a 1D approach, so you have to account for how the percentage of the cloud coverage. So 0.3 is the current Earth value. But then the transmission climb quite a lot, and the absorption a little bit, and then you have the heating factor here. But as I said, it really depends on the cloud, and if everything would be equal, you put 0.4 here, you're cooling again. So it's not easy to know a priori. Let's talk quickly about the effect of circulation on cloud. So obviously, the cloud coverage is really correlated to the circulation. I took this cloud coverage plot from the Tony's website, the models he provided for our activity, so that rocky 3D simulation clouds, and I mean, it's obvious that the clouds are correlated to the circulation. Another effect of circulation, I mean, not directly on cloud, but how we apprehend the cloud modeling would be this famous KZZ that we talked since Tuesday, and Ted talked nicely about calculation of this coefficient. So that's really to evaluate the efficiency of the vertical mixing. But how to really calculate this thing? So a crude approach would be to have the root mean square of the vertical velocity from the GCM multiplied by a length, which is roughly the pressure height scale, but could be lower than that. So Moses calculated it with the Spark MIT GCM. Another approach is to use passive tracers. Vivien wrote about it, and Zeng and Schoman extended a little bit the formalism with MIT GCM Spark. And Benjamin also used this approach with LMD GCM. So in this case, we take the averages of the density, tracer abundances, and the vertical velocity divided by the averages of this quantity here. And so that's what you get. So the blue line is Moses calculation here, and here you have the different tracers values, and it turns out that you can approximate that by per law of minus 0.5 in pressure. Just so you know, the Benjamin's value would be more like minus 0.4. So it's also hiding the fact that you put a lot of things in the GCM, and that it's obviously model dependent. All fine. So now we would like to talk a little bit more ways to implement cloud. So as I said, if you have a GCM, so I talked briefly how to calculate this KZZ. Now I'm looking more broadly on models and clouds in models. So the first thing would be in 1D, for example, what Vicky presented. So in the climate model, so it's not like I mean, the circulation is kind of prescribed, but then so in these models you have radiator transfer, so include chemistry, molecular opacities, and so on. Convection prescription for the convection, and obviously cloud. So in this case, either you prescribe a size distribution, or you calculate this distribution if you have a photochemistry model, and then you calculate the radiative effect usually through mid-theory. So you get from databases extinction and scattering the refractive index, real and imaginary. So here are a few examples from Daniels for the CO2 and Wakeford and Singh for a few like silicates and so on. So that was more terrestrial planet and more hot Jupiter ones. So you hopefully you get measurements or databases for your molecule, and then from the theory you calculate the optical values you're interested in. So wavelength dependent, or like optical depths and so on. And in some case you can already relate that to measure of the planetary radius, or like applicable to transmission spectrum. So that's really what you can do in 1D model. It's really calculate the radiative effects on that. So if you want to implement cloud, or if it is already implemented, I have to say I first wanted to try to compare a few GCM and how they approach the cloud parameterization. But as Daniel told yesterday, the what makes clouds and the grid of your GCM are, I mean, the grid of your GCM is not able to really reproduce that. So you really have to parameterize that, and it's not easy to find the information. At least it was hard for me to go say, okay, so let's take this GCM. What parameterization did you use and whatever. So instead of comparing or try to see understand the differences, I just put the manual or the documentation of the GCM I use. So you see that you have relation with like a hard-coded number here that comes from a relation like empirical or some. I mean, you can see right away that it has really been tuned for Earth. So I'm always wondering of the validity of this approach for other planets. So I'm not sure myself, and I would like to see more, because when you for example have two models for Proxima B or something, and they are not the same, okay, maybe the cores, but they always invoke the cloud parameterization, and it's hard for me to get really this difference where they come from. So let's understand how you parameterize your cloud in the GCM, and then hopefully try to understand the difference with other approach. So here I'm switching them more on hot Jupiter. So of course Vivien will come right after me to talk about it. So I hope to not take too much of his material, but it's just a way, like, if you want to implement clouds in your GSM, so a few of the approaches then. So the simple approach is an equilibrium approach. Then, so you calculate your temperature structure, and if you cross condensation curve, then at that point from upward, you're condensing cloud. So the top of the cloud and the size of the particular parameterized in this model, but that gives you an idea of the spatial distribution of clouds. So here are some results. When after what he did, he post-processed this cloud distribution to radiative transfer, and that gives you flux. So here in the Kepler band. So in this radiative transfer, again, the meteory has been used. So you can see like reflective clouds and the lib and so on. I will not say so much more, but that's a nice and easy way to introduce cloud into our hot Jupiter circulation models. Another approach is to use the 3D structure and post-process that to a more complicated cloud model that include the microphysics. That's one Christian is making us doing, and that's also been published by Graham. So you take several 1D path, and so that you get the temperature, a velocity structure. From this you get this KZZ again, and once you get that, you push that into the cloud microphysical model, and then you get all our quantities here. So albedo, so you get maps of albedo and radius, I mean size, and so on. So in also with depth. So, but in this case, we didn't really, I mean, it was still decoupled, right? Another way is to include microphysics, but inside the GCM, but then it's also need to be simplified. So that's what Benjamin did. So for warm Neptune, we included condensation, evaporation, transparent sedimentation in his model. Also parameterize particle size and also get the particle, the spatial distribution of clouds, and so obviously vertical abundance profiles and so on, and you get effects of the size you choose on the spectra, obviously. So the last thing I want to say is that we are almost there to really try to get to the full thing, like having the microphysics inside the GCM. So that's been done by Graham and collaborators twice. So it's really trying to consistently calculate all of that, the circulation, radiative transfer, cloud microphysics, and the feedbacks of the clouds on that. So there are a couple of models who did that, and that's, in my opinion, the state of the art, but it's not obviously affordable for everyone, of course. So yeah, so I conclude here with yeah, you can pick a method of including cloud in your GCM.
Questions? Okay, if nobody has a question, I have a question. What do you think is the right balance between complexity and simplicity for cloud models coupled to GCMs?
The important thing is always to understand what you put in your model, right? So me, in my personal case, I have currently no cloud, so I will start with Vivian's approach, or just condensing them. But yeah, I guess there are for every flavor for everyone, right?
Tony?
Yeah, totally agree with that. Yeah.
Just following up on this point, I was wondering if is there a certain set of benchmarks that everybody runs or test cases, or is done on a one by one basis?
Yeah, I mean, not for clouds. I mean, each one does this thing, and that I find it hard for that. Yes, as I said, that for Jupiter I don't have clouds, and for terrestrial planet I have clouds, and I show you that, and it's hard for me to compare to other people. So. Please. Thank you.
Any other questions? All right, if not, let's thank Nicola again. All right, next up is Vivian Parmentier asking, do we understand what's going on at all?
Hi all, thanks a lot for having me here. I just began an assistant professor at Oxford University. So that's your reminder, but Pat just did it before, that real clouds are like this. So that's like a small scale Juno cam image where you see this small like convective clouds on top of a white cloud with reddish cloud on the side. And that's GRAM image at around 5 micron from Juno, taken from far away in the orbit. So you see clouds in the great red spot here. So clouds, at least on Jupiter, right, they're inhomogeneous at the small scale, inhomogeneous at the large scale. So we really have to keep that in mind. So yes, why are we here discussing clouds on exoplanets? I think the first reason is because we think that we see clouds on exoplanets, right? So I try to get you a sense of what are the actual evidence for clouds in transiting planets, and mainly hot Jupiters, and whether there's strong evidence or not, and whether we actually understand what's happening. And this is not working. Yep. Why don't we just switch like this? Okay, so we'll do two things. We'll talk about evidence in transmission and evidence in phase curve. I think that's the two places where there's most of the evidence. You can again. Okay. So transmission spectra, how does that work? Some people might still not be completely familiar with that. This is an example from home. This is Earth, taken by satellite Imawari. And it's a weather satellite supposed to look at, directly down. But sometimes they like to make nice pictures, so they look at the moon rising at the limb of it. And the nice thing is that it has multiple wavelength bands, right? So if you look, if you take the image at 8.6 micron, this is what you see. So you're seeing the cloud deck here. But if you go then in the ozone band at 9 micron, what you see that the atmosphere actually looks bigger, okay? So that's the main reason we can do transmission spectroscopy at some wavelengths where the atmosphere absorbs. The atmosphere actually look bigger, and the planets look bigger. And so what do we expect for a nice behaved cloud-free atmosphere would be something like this. So this is back 2010, models by Fortney. And there's a Rayleigh scattering slope at short wavelengths. The sodium here and these potassium lines, and this would be water lines, and if you go to the infrared, then all the molecules starts to kick in. And so sure enough, we took telescopes to observe that, and that's right, the first, one of the first observations of a transmission spectrum of an exoplanet. So we don't see that, we don't see that, we don't see that. What the heck? So people back at the time were pretty pragmatic. They were like, yeah, maybe that's, Rayleigh scattering due to aerosols seems to fit reasonably well a slope here. And you can actually fit that because if you believe it's Rayleigh scattering, you're pretty sensitive to a particle size. And you can say like, yeah, submicron particles should do the trick. But what's nice is that if you got higher resolution, you actually see the sodium in this planet at HG18973b. So at high resolution, the opacity of the sodium is large enough that you're seeing higher than the supposedly happening clouds that's on this planet. And so that's the Singh et al. Plot. I'm missing the reference, but it's David Singh's Nature paper, 2016, I think. That's most of the transmission observation we had back at the time. And you can see, yeah, that we have a bunch of slopes here for all those guys, and they're all different. And so, yeah, in the near UV, that's what we kind of first claim as evidence for clouds. And there was some hope, because depending on, that's work by Anna Wakeford, depending on basically how the grains, the molecules that compose the grain, they have links, so if they have SiO links or ILO links or whatever, they're gonna have both spectral features in the infrared that are different, but also slopes here that are a bit different in the optical, because some clouds might have some absorption bond, basically, a bit in the optical. So there was some hope that we could use the slopes, right, to actually say something about the cloud composition. What do we actually do usually? So this is data for HD189733b by Pont et al. And McCullough 2004. Space data, all of this. So that's what the spectrum looked like. And the order 0 fit to that people used to do was like, okay, that looks like a slope, so let's fit a slope. And that kind of looks like flat, so let's fit a flat line. And maybe we have some stuff poking out a bit above, so sodium here and water there. And indeed, when you do a nice 1D retrieval, that's Barstow 2017, and honestly, most retrieval codes for now, they basically do that for the clouds. They have some parameterization for the haze, and some parameterization for a cloud deck, and you just fit those parameters. And you can get a pretty decent fit to your spectrum. But then, right, Christian told us clouds are complex, and that's not telling you much. So let's try a more complex approach. And the more complex approach that's been done for this planet up to now is to run a full global circulation GCM plus a 1D macrosophysical scheme inside, and to mix everything, and you have the seed forming, you have the sedimentation, you have the growth, etc., and you get the green line. And the green line doesn't fit the point, right? So what's happening is that the green line is actually making way too much clouds too high in the atmosphere. It's making big particles too big, so the slope is very shallow, and they're pretty high, so you completely wash out the water feature that was there. Okay? So that's based on at least one assumption that of what you put in those 1D models, right? So maybe it's not silicate. Like most of the clouds forming here is silicate cloud. So there's different possibilities for not having silicate. So one point could be another cloud species. Like for some reason, the magnesium is not here. It's been called trap, and maybe something else is taken in. It makes a smaller cloud mass, and so you could mix it up more. So that's one possibility that's not tested for now. Another possibility that was tested recently is to have some photochemical hazes. So in that case, that's a paper by Lavas 217, a 1D paper. They actually form some fluffy small haze particles on the top of the atmosphere, and the stuff coagulate and settle down. And the good point with haze, right, is that because you form them on the top, then you have small particles on your upper atmosphere, because that's where you actually form them. And they get, some reasonably decent thing. They can get a hazy slope with water abundance here. The only problem is that to make those photochemical hazes in this model, they need CH4. And when you look at the transmission spectra, you should see CH4 here if it was there, and it's not there. So there's no CH4, so you can form the haze. So what's going on, right? What Ben Rackham was telling us, and he has a poster on it, and it's been something that people have been looking since the beginning of transit observations, the effect of stellar activity on unocculted spots. And they can actually mess you up a lot, the optical slope that you have here. It's basically if your planet crosses a part of the star that is not representative of the mean brightness of the star, so you have spots, more spots outside of transit than inside of transit, then you induce spectral feature in the transmission spectra because, and you can see that for here, a photospheric and spot contrast, that's not that big, and you can play with the numbers, and you can see how the slope is actually changing widely between that and that. So probably, right, a combination of the stuff. But this is to consider that slopes themselves are going to be, for now we don't really understand them, and they might be mixed up partially with stellar heterogeneity. Okay, let's go a bit at longer wavelengths. In the optical, we have the sodium lines and the potassium lines, right? And that's pretty nice because what the theory predicts is that if you have a cloudless atmosphere, you see those big wings here, okay, of the sodium. It's thermal broadening for sure, and maybe a bit of pressure broadening, that's broadening the lines. And so in some cases, like we saw HD189, we definitely don't see those lines. But in some cases, was 17, I think? 19, 17? Okay, I'm not sure, sorry. I should have written it. One of the WASP, the cloud-free WASP, by Nikolov 218. And you can, I mean, right? Yeah, something. It's broad, it's not flat, it's broad. It's definitely not compatible with that line, but more with one of those lines. So yeah, you know, seeing the sodium feature can actually be a good telltale of whether you have clouds or not in your atmosphere. And that's not going to depend on your stellar inhomogeneity as much as the slope itself, because you're actually resolving a feature that's not supposed to be too much on the star. And by the way, that was actually the fact that observing a sodium line that's not wide enough was already a clue of clouds in the first detection of an atmospheric feature in an exoplanet by Charles Bruno 2002, where he was indeed saying that, oh, sodium is too small, what's going on? Maybe clouds, maybe something else. I think we're still roughly at the same stage now, with slightly better data. Okay, we keep going between 1 and 2 micron, right? That's a fabulous instrument, HSC-WFC3, that was mounted while I was undergrad. I remember seeing the astronauts pulling out NICMOS and plugging back WFC3 inside the telescope. That was awesome. So we can observe the water, basically. And that's what we observed, right? That's Deming et al. 2013. One of the first, maybe the first use of WFC3 for this. That's water absorbing, that's water not absorbing. And something that's pretty nice is that you can, it's been done since 2008 or even before, you can write analytically what you expect transmission spectrum to look like. And the funny thing is that the radius difference here depends here on the abundance times the cross-section of the species that absorbs here, and divided by the abundance times cross-section of the species that absorbs here, okay? If you assume that water and water is what's actually absorbing here, you're seeing the top and the bottom of the band, the abundances here goes away, because A equals B. So it's just the ratio of the cross-section. So what this is telling you is that at order 0, transmission spectra on a short wavelength range is not sensitive to molecular abundance. Funny, right? And actually, that's true. If you make this calculation, you find that the water abundance should be bigger. The water signal should be bigger, whatever the water abundance you choose. So what's going on? And so it's not as big as it should. And this is a plot of theoretical size of the water feature as a function of the observed size of the water feature for a bunch of hot Jupiter by year 2016. And that's the one-to-one line. And so you see that they're all systematically smaller. All hot Jupiters have a smaller than expected water feature. So you have several explanations for that. So one explanation is that this formula is no more is applicable, but actually the abundance here is no more the water abundance because I'm no more probing water here, but something else. Could be H2. Maybe I don't have a lot of water and I run into collision-induced absorption. And that's very nice if you put that in a retrieval because you can measure actually the ratio, you know, the ratio of the cross-section, so you can measure the ratio of the abundances. So you can measure the H2O over H2 abundance ratio, which is, you know, kind of what you actually want at the end. That's like metalysis. Well, that's what you want. And that's the answer you get here is that because H2, you know roughly how much H2 there's in the atmosphere, you know, those are presumably H2 balls. So you really need not a lot of H2O to make that. And that was back at Madhusudan 2014 A and B, where the claim was that most of those hot Jupiters actually have water-poor atmospheres. That was basically driven by these WC3 retrievals. So there's another possibility, right? Maybe it's not H2, maybe it's clouds. There's a cloud deck here. And so now we're stuck a bit because I'm measuring H2 over the cloud abundance. I don't know the cloud abundance. Clouds are complex. I think we learned that. And so I can try to marginalize over it. And that's a retrieval of this data by Björn Benecki that should publish this paper. And so you can change the cloud top pressure up and down, and you can change the water abundance, and they follow each other. If you put more clouds, then you just have to put more water, and then you get the same feature. And you see that you get 4 orders of magnitude uncertainty on water abundance and 4 orders uncertainty on the cloud top level. And the limit here is when the clouds go below the H2 collision-induced absorption. So you can go below that, because then you eat the H2 CIA. So there's no way you're going to continue this. And here we'll see that's the high mean molecular weight limit. And so for a while, just with WC3, you basically can't get better fits. If you talk to Ryan, and I won't talk that too much here, if you actually join fit WC3 and the optical data with a lot of caveats, then you can actually narrow down a lot the water abundance least posterior. But I think, yeah, that's going to be the future of retrievals. So the other possibility is that the molecular weight is large, and that's having a fun effect of the spectrum. It's not cutting it, it's changing the scale height. So you're actually squeezing your feature. So the shape is a bit different than it is if it's obscured by clouds. And what's really funny is that the shape is exactly the same if you have a partial cloud coverage, meaning that your part of your atmosphere have clouds, part is cloud-free. Then you're actually assuming a cloud-free on the cloudy spectrum, and make the average, and you get a squeeze feature too. And for mini Neptunes, that actually is super important because that's data for hat P11b that you see here, the WC3 data. And when you do a retrieval with a 1D model, then it points toward that this planet is a high mean molecular weight and doesn't have clouds. But if you include the patchy cloud hypothesis inside it, then your posterior completely changes. And the best fit is now a solar composition planet, but it's half cloudy, half clear. So how do you make this partial cloud? I identify 2 ways to make partial cloud. There might be more. We can discuss about that. The first one is circulation-driven partial cloud, which is basically like on Earth and most planets on the solar system, circulation-driven. And this is simulation with tracers that are passive tracers advected in the atmosphere. And you see that you can clear up the equator, for example, from clouds, from an HD189 planet. And this is when the radiative feedback of the cloud is included in the model by lines 2018. And you can get crazy patchiness on the day side, and that makes you crazy phase curves in Spitzer. And this is disturbing. And so the second way to form partial clouds is temperature-driven. While the circulation-driven should always be there, because there's always going to be a circulation on those planets, temperature-driven partial cloud might not always be there, because for that, you would need big temperature contrast. This is happening. This is going to happen when some parts of your planet are just too hot to form clouds, and some parts are cool enough to form clouds. And so to have that, you need large temperature contrast. And you can kind of understand that to have large temperature contrast, you need your parcel of gas to cool faster than it's advected around the planet, or your parcel of gas to cool faster than the planet, than the sun is rotating around the planet, if you're not tidal lock you're seeing. And so that's the radiative time scale as a function of temperature. And that's basically 1 day at around 1 bar-ish. And so you can see that you're expecting basically big temperature difference for everything that's above a certain K in TX. Below a certain K, when you go to the mini-Neptune around M-dwarf kind of planet, you might be more homogeneous. But above a certain K, you're definitely going to have temperature contrast. One such example is HD 189, HD was 121b, sorry. This is the limb temperature taken directly from a GCM simulation of WAS 121b. This is the west limb, it's colder. This is the east limb, it's hotter because winds are blowing from west to east. And I've added here equilibrium condensation curves of a bunch of condensates that we think could form in this planet. And you can see that the temperature contrast between east and west limb is like 1,000 K. It's big. And that's enough for, on the east limb, I don't expect any clouds to form. It's way too hot. Any particle is going to evaporate. Whereas on the west limb, right, I get this whole region that's cold enough that everything should condense. So you're crossing really a lot of condensation curve. And if you look at the spectrum, this GCM with those clouds do the green line, so they do a better job than this GCM without the clouds, which do fully cloudless. So partial clouds are a priori expected to be there, and they do a reasonably good job at explaining the features. Obviously, it's probably a combination of both, right? If you look at Graham Lee's work, Lee et al. 2016, this is a cloud map on HD 189, and the model he's using is actually making the day side quite hot compared to others, and hot enough to actually evaporate the day side clouds. So you get both this like depletion of clouds by the dynamical mixing at the equator and the evaporation of clouds on the day side. And so if you were to plot, so this is a small simulation I made myself, if you were to plot the reflected flux from such a planet, that would be what the day side would look like, because so no clouds at the equator because they were kicked out, and no clouds here on the east because it's too hot. So you would have two bright spots there. And we'll skip that because there's not enough time. You can talk to Ryan how he's solving all those problems. Infrared for now we have Spitzer, and for now Spitzer looks kind of flat in transmission, so it's not super informative. But soon we'll have James Webb, MIRI, and MIRI is awesome because you could either see through the clouds or see molecular feature of clouds or see black body, and that's going to be boring. Here, that's a kind of optimistic model by Wakeford 214. That's basically telling you if the slopes that we see on the opticals are actually due to very small particles of silicate clouds or whatever, then in the MIRI bandpass, you should see huge silicate features, huge spectral feature of those clouds. So there's a big if here, right? So we talk about the slopes, we don't understand the slopes. But at least we're going to be able to test. If we see those big silicate features, yeah, somehow those atmospheres are made of 0.1 micron super small clouds, and we have to update our microphysical model to actually get that. Okay, I don't think I have much time left, but we'll talk a bit about phase curves. Thermal phase curve, that's a nice cartoon made by Tom. Tom, you're here, that's you. So the planet goes around the star, and you can see the day side and night side in the optical. And what we actually can measure is the amplitude of the phase curve that's related to the day-night contrast in temperature, and the offset of the maximum of the phase curve that's related to how the temperature is distributed with longitude. Okay, good. So we've seen a bit of that. That's an example of a global circulation model output for hot Jupiter. Temperature map. And so you have this super rotating equatorial jet that's basically changing the hot spot instead of being at the substellar point. The whole temperature map is shifted a bit to the east. And so the maximum, the hemisphere, the hottest hemisphere is centered at the cross here, and the coldest hemisphere is centered at this point here. And so yeah, the GCM kind of capture this behavior relatively well. And this, what I'm overplotting here, is a condensation curve of one species. So there's you can imagine that if your temperature map is shifted to the east, right, it means that some species are not going to be happy here. So if you add a cloud, you might expect a cloud in the hole, the cloud deck to have a big hole in it that's actually shifted like the temperature map. And from the phase curve data, what you can do, as we say, is measure amplitude of the phase curve and phase curve offset. And different points are different wavelengths. And you can plot that as a function of a quantity. Here, the equilibrium temperature, and you can expect to see some trends. And do you see a trend here? Who sees a trend in this plot? You see a trend there? It's a bit better here, right? We'll come back later. That's what the GCM does. Okay, if I plug my GCM and just run different TX, then I can measure what it spits out as amplitude and phase curve offset, given all the assumptions I gave him, and that's what I get. So I'm seeing a trend in the GCM, a trend that's very nicely explained by Tad's analytical model, for example. But I'm nowhere matching the high amplitude that I'm seeing. Okay, and as Daniel was saying, the high amplitude that I'm seeing are actually due to cool to dark night sides. And I'm always overestimating the phase curve shift. Like always, right? This is a pretty big discrepancy. So my GCM models, cloudless, give me a qualitative understanding. You know, I have the inner contrast, I have a phase curve shift, but not a quantitative one. So to go a bit further, you can look at other wavelengths. And so phase curves by Kepler did a bunch of phase curves, and that's one of the examples. Okay, Kepler 7b, the first one that were pulled out. So you had to integrate for 3 years of phase curves of a planet that's on a 3 to 4 days orbit to get this data. So don't expect to get many more of these before plateau, basically. And, right? Where's the maximum? Here. A bit this way. It's definitely not this way. It's more this way. And that's the exact opposite from what was seen from the thermal phase curve. Okay? So Kepler phase curve has shifted one way, and that's indicative of clouds on the west of what we were saying, an anti-correlation between the cloud map and the temperature map. So how does it look like in real life? So Kepler phase curve offset as a function of TX. There's 6 planets with it. And when you plot that, right, you want to do this. Do you want me to do that? Would be good, right? Okay, first order of the understanding of this plot is that this is thermal emission, that this is reflected light. And I can show you that here by showing you a phase curve at 1900K. That's from a GCM model again. You have the hotspot offset here that's bright enough to spit out flux in the Kepler bandpass. This is the clouds on the west limb that are bright enough to actually make some reflected light. The thermal phase curve look the red, the reflected phase curve looks the blue, and the sum of the 2 phase curve in the Kepler bandpass looks like the black. So this one is roughly a 0 offset. If you put your planet closer to the star, you increase the temperature. The flux of the temperature is going to go as T to the 4, whereas the reflected flux is going to scale just as the distance, directly as the distance to the square. And so if you go closer, this one goes up, this one goes down, and your thermal emission dominated, and you have an offset this way. If you put your planet further away, then thermal emission is going to die. It's going to get out of the Kepler bandpass, and you're going to be determined by reflected light. And so the first order, right, is that this is thermal emission, and so it's the good way, it has a positive offset. This is reflected light, so all reflected light dominated planets have an offset that tells you there's clouds on the western side. So how does, okay, let's talk about a bit of poetry. Okay, imagine you're on a spacecraft, space mission. Laura just posted on Twitter a plan to visit all the planets, and I added the exoplanets for that with the next mission. And look by the window, this is what you would actually see. This is the GCM grid I'm run, and I post-process it, not in the Kepler bandpass because that's boring, but in the optical bandpass with the colors matching what you would actually see. So we can do a bit of funny radiative transfer here. First, remember I told you that all those clouds have slightly different slopes in the optical. Some have absorption features. And so the clouds, this is the cool planets. They're fully cloudy. And you can see that the clouds are actually different colors from your eyes. This is because the opacity and the optical change as a function of cloud composition. In the hot case here, this is, so temperature increases that way, cloud composition changes that way. In the very hot case here, you're beginning to see the planet glowing. It's so hot that it actually emits light in the Kepler bandpass, but also in our eyes. The Kepler bandpass is roughly the same as what we're seeing. So Kepler is seeing the integrated light of those blobs. In between, it's pretty neat, right? This is pretty blue. We have blue planets. Why do we have blue planets? Because sodium. Because sodium absorbs a lot of the red, and so sodium potassium absorb a lot of the red, and so you get more blue. So you have a sky that's even bluer than Earth. And so what you can see, right? Large TX, no clouds, makes sense. Small TX, the planet is cold enough everywhere to form clouds everywhere. And what seems that the observations are telling us, right? Because here you wouldn't form an offset, because right, there's no longitudinal variation in the cloud cover. Here you wouldn't do an offset the good way, because it would be all thermal dominated. And so what the observations are telling us that most of those guys are actually living on this band. We didn't find planets like this yet. Maybe we will. But in the Kepler sample, and I'll show you an albedo plot later, there's no planet like this. So the observations are telling you that you're roughly partially cloudy. And that means, right, that you have to change the main cloud composition has to change as a function of TX. So hot Jupiters, we put them all on a big box. But those guys have a range of temperature that goes from T dwarf to M dwarf. Like brown dwarf people have like 20 classes of brown dwarf in this range. We call them hot Jupiter. So there's going to be a huge diversity, and probably a diversity in the cloud composition that's actually on those planets. Does it work reasonably well with data? So this is the data I showed before. And this is the outputs from the model, phase curve offset as a function of TX. And it's, when I made this plot, I didn't believe it at first, and that's what the model gives. Impressively, it does fit data. You know, sometimes it happens. And I think that's telling us something is that really this phase curve offset here on this cloud is determined by the radiation and basically by like the radiative timescale, because that's how far you can shift your temperature map to the east is determined by the radiative timescale. And so it's really determined by like a small number of physical parameters, whereas transmission clouds, you need the cloud height, you need the cloud particle size, there's many more microphysical parameters that are going to happen. But when the clouds are determined by the thermal structure, then somehow the problem becomes simpler. I think that's what this plot is telling us. Maybe I'm wrong. Obviously, if I put all the clouds, as we discussed, that's not making any phase curve at all. And so I need a way to make them disappear, right? That's what we do. The observations are telling me the clouds are not the same as a function of TX. So but it's cold enough to form silical clouds here, so there must be a way so that they don't form. And so one way you can think of is come back to the figure Nicolas was showing. And there's a fundamental difference between brown dwarf and hot Jupiters. That brown dwarf are all illuminated from below, right? Hot Jupiters from the top. So if you plot a representative PT profile for hot Jupiter, so P goes down here and T goes up, so it's the same as this. So brown dwarf looks like that, okay? Hot Jupiter, because it's illuminated, it's gonna look something like this. You're stabilizing the atmosphere here, and you have a quasi-isothermal layer, basically. Now, if I had a condensation curve here, Let's go there. I can have several ones, I guess. So I could have, you know, condensation curve like this. So here I would expect, right, clouds to form here for my hot Jupiter, clouds to form here for my brown dwarf. We're fine. Now imagine, okay, that was a poor drawing. We need the brown dwarf to be slightly more tilted. I'm cheating now. Okay, let's say the brown dwarf looks like that. And so now I'm making a condensation curve like this, right? My brown dwarf cloud is going to form here, so I'm going to see it. My hot Jupiter cloud, one cloud is going to form here, but that's a day-side profile I plotted, right? A night-side profile on a hot Jupiter is going to look, if you look at it, so I look like the blue curve is like the night-side profile. It's going to look much more like the brown dwarf cloud profile. But if I trap all my clouds here down, right, I would think I would make a cloud on the night side of this planet, but maybe I don't because the cloud material is actually at 100 bar and cannot come back. So that's kind of the argument we try to push, because we know that stuff are well mixed from 1 bar to above, from like tracer studies and stuff. It seems pretty well mixed. And it might be, so if you put clouds here, it's going to go everywhere on the planet. But it might be poorly mixed down here. So if you put a cloud here, maybe it cannot cross back to be visible. And so if you do that, which is basically each time my PT profile at the deep layers crosses a cloud condensation curve, then I remove that from the mix. Okay? I say, oh, wait, here, my TIO cloud, my equilibrium chemistry would tell me that it would form here on the night side and a bit here on the top of the day side, but I think they form deep down and they're no more available for condensation. All the gas has been trapped in clouds in the deep layer of the planet. And if you do that, which is a pure forward model approach, then you get the red curve, meaning that the clouds go away at the right moment compared to what I want the observation to do, or the model to do. Okay, so I think that's reasonable evidence for the presence of a cold trap. Then you can argue it's 4 points, right? Certainly 4 points is the lack of high albedo planet. If you looked at the same plot, Kepler phase curve set TEC, that's albedo as a function of TEC. Two models, one where I have both MGSIO3 and MNS clouds. And so here I don't see any more offset because it's basically dominated by MGSIO3. And here in the albedo, right, what happens? I ensured all my planets in silicate clouds, it becomes very bright. And we detected planets here, low albedo planets. There's at least 3 low albedo planets in the Kepler sample that are around 1500K. So if the majority of hot Jupiters had were enshrouded in silicate clouds the whole day side, we would have seen them here. There's no way we would have missed them with Kepler because we saw this is a smaller signal. We should have seen the higher signal one, and we didn't see anything. That's telling us something. That's telling us there's actually no planet here. So does this cold trap approach works? So you can ask microphysics people, like, yeah, let's try to make a cold trap. So that was done by Diana Powell. That's a karma model, so it's a microphysics model. It's actually resolve the size of the particles. It makes size beams instead of using the momentum equation. So you can make those plots, which are pressure in the atmosphere and particle size. And that's the number of the abundance of your cloud inside each of those beams, right? And she did 2 cases, a high entropy interior, which means, let's imagine that something's heating up those hot Jupiters, right? They're inflated. So let's imagine that instead of that, I'm completely wrong. What's actually happened is that the hot Jupiter is like this. Okay? We call that high entropy interior for some reason. In that case, no more cold trap. I'm avoiding the condensation curve at D, and I form one big cloud here. So we're only using MGSIO3 and TIO2. So TIO2 makes the seeds, MGSIO3 condense on it, and you form one big cloud. Now, if we use this little profile, the one from the GCM, right, we form 2 clouds. That's the cold trap I was talking about, right? A bunch of stuff is trapped here and doesn't make it there. However, I still have a big cloud here. So our 1D model for now is telling you, oh, there is a cold trap, but it's not efficient enough to remove the silicate clouds from your atmosphere. the upper atmosphere. So maybe we're just using NGS0C and TO2. If we were to put a whole bunch of stuff like iron or things like this, you would increase a lot the mass of clouds. That would make bigger particles. They would settle more, and the cloud trap might be more efficient. KZZ is basically unknown here, so we have the KZ approximation that matters. So whether basically, what's I think is really interesting here is that observations could tell us what the deep PT profile of hot Jupiters look like by looking at the clouds. If you actually detect silicate clouds on very cold planets, it means that the TP profile is not crossing the condensation curve. If you stop detecting it at some point, it means that maybe they're being trapped in the deep layers. So what did we learn on how does that compare back to the thermal phase curve? What we learned is that most of those hot Jupiters are probably partially cloudy, which means that to first order, they have cloudy nights, clear sky days. For the limb, it's complex, but first order, cloudy nights, night side days is cloudy nights, clear sky days is pretty good approximation. So you can run models with that approximation, like GCM models again, and that's what if I do that, I enforce clouds to be there on the night side. I don't care who's forming there, is there a cloud trap, is there what I'm saying, like it seems that observation is telling me I'm cloudy night, so let's do the cloudy night. And that's how the cloud, the amplitude and the offset of the phase curve change with particle size. So depending on the particle size I assume for the cloud, then I get larger and larger amplitude and smaller offset. Oh, right? I do get closer to that. So maybe the spread we're seeing here is actually the spread in microphysical cloud quantity, and that's the second order thing that we're going to need to understand. And for that, we're going to need highly complex models. But to order zero, the cloudy nights, cloudless days is a reasonably good fit. Well, not at all for that, right? I never get those small offset. So those very high temperature planets, something's going on. Magnetic field, you can always wave your hands and say magnetic field. Might actually stop the winds and make very small offset. So we need to measure wind speed, and that can tell us what's going on. Night side clouds, will we be able to get a proof of that? Maybe, James Webb, this big thing that's going to launch one day. Do some models for WASP-43b. So WASP-43b, if you come back here, is this pathological case, right? It's like well above in amplitude than everybody. Basically, we didn't detect night side flux for this planet. Some people think that they detect night side flux. There's some reanalysis of the data here by Mendoza, where they think that they do detect, but it's dim anyway. And so one way to make it dim, right, use our spectrum, appear star as a function of wavelength for the day side here, okay, and the night side here, for different kind of models. So the clear solar model is this color, and so what happens, this is a zoom in the WC3 bandpass. The clear solar model is here, gives a not too bad fit to the day side spectrum, but it overpredicts by a wide range the night side spectrum, right? This is not what's happening to the guys here. It's not as there. If you add night side clouds, if you add MNS clouds, they evaporate on the day side, they condense on the night side. So your day side spectrum is basically the same, roughly, but the night side spectrum is dimmed out a lot. Okay. If you put silicate clouds, they form both on the day side and the night side, because the planet's cold enough to have silicate clouds on the day side, and that completely makes you wrong on the day side, but it dims you the night side even more. But if you look, all the models that are very dim here, right, the red and the blue guys, they dim, and the speed there, it's like, now you won't see anything. Even with James Webb, this is going to be really hard with near-Earth or things like this. But if you go past, right, 5, 6 micron, then the cloud opacity becomes smaller, and here's where your flux is coming out. So MIRI is the one that's going to be able to see the night side of these planets and to get some insights about what's going on. This is spec observation that we're planning with the Veno detector. So guess it's time to conclude. Hot Jupyter clouds are going to be really complex because on top of the microphysics, the vertical mixing, on top of all the complexity of the 1D stuff, those are inherently 3D. So you have to keep that in mind. The 3D lashes sculpture is going to be fundamental. As I say, partially clubby limbs are definitely what's going on, I think. We do understand some order 0 stuff. There's also order 0 stuff that we don't, like those slopes. We have no idea how to reproduce them. There's very likely a cloud sequence with TX. So stop thinking about hot Jupiters as one class of planets. We're gonna find a way to define them better. Generously, which would be awesome. Thank you.
Questions?
I love your cloud family ordering. Can you go back to this map? Yeah, give us a zoom on. Yeah. So if you say that your planet has corundum clouds, what does it mean?
If what?
So one of your planets says 1000 Kelvin and A203. What does it mean?
Okay.
Does it by, yeah.
Can you repeat? I didn't hear you well enough.
What I'm wondering is, does that mean the entire cloud is made of
Yes,
mainly
okay.
corundum?
Yeah, so the way these models are made, it's the simplest way. That's why it's impressive. It actually fits anything. I take the temperature map from the GCM, and I post-process it, assuming chemical equilibrium condensate clouds with basically infinite KZZ. So the clouds just fill up the space, and I choose one particle size, monoparticle size, and one species.
But then I think you can't draw this conclusion because each of these clouds will be a mix of materials, and in particular you will have iron in all sorts of ways in there. Because if you have corundum, if you have Al2O3, it's a high temperature condensate. This means everything, all other high temperature condensates will be present. And what is more serious actually, if you say you have barium silicate clouds, this means all the high temperature condensates will be present because they will be thermally stable. So it means your silicate clouds will be far darker than what you presently can show.
Yes, the albedo are probably overestimated here.
Yeah.
But do you expect to have fully cloudy day sides with a mix of stuff and get, right? Because if you go back there, one of the arguments, right?
Yeah.
I guess that's what you're referring to. I'm claiming that we're not seeing those bright planets. You're saying, yeah, but it's never gonna be that bright anyway. It's gonna be darker clouds.
It will be darker.
Do you go dark below like 0.15?
I don't know, one needs to do the calculations,
Yeah,
but it's
definitely.
surely not, the models surely don't, I mean, saying that the models show that it's magnesium silicate clouds, it's wrong. Because it will be a mix and it will be darker.
Yeah.
Especially if you have iron in it. Iron is a nightmare.
Yeah.
From the exercise on Tuesday, we saw
Really dark stuff.
Yeah.
No, that's a very good point. This is telling you that there is no pure silicate cloud
Absolutely.
atmospheres below 1500 K. And maybe
Yeah, that's true. Can you go to the Powell plot?
this guy.
Yeah. No, the other one, which has the detached clouds.
Wait, the karma thing.
Oh yeah, like the Hamas.
Okay.
Yeah, that's a wonderful study. But you also can show that if you have a diffusive atmosphere, you also form detached clouds. So you don't necessarily need a cold trap for having different detached clouds.
You don't need to cross the condensation curve twice to form detached clouds. That's what you're saying?
Condensation curves.
No, okay.
Yeah.
You don't need to reach supersaturation larger than 1 in 2 places separated by a subsaturated
I
place.
think you are again trapped by the fact that you only consider one material. If you have a whole zoo of materials, you easily, due to
It might be.
easily, and this is what Mark Becky has shown here, can form various layers of clouds, which also are proposed, but
the KZZ are really big in those stuff. So because to my sense, to form layers of clouds without cold traps, what you need is small enough KZZ so that the clouds are not gonna mix with each other. whereas here you really have big cases. So it seems that you need something more drastic, like a contract to separate the cloud layers. But it remains to be tasted, I agree.
What fraction of the sink slopes can you just fit with Rayleigh scattering?
Oh, just the slopes themselves?
Like the slopes on the very
I mean,
short.
the problem is that you don't know where you're probing. So if you just have the pure slope, you can basically fit most of them with Rayleigh scattering.
So do you consider any of them evidence for clouds then, or?
I think the evidence for clouds comes actually more from the fact that you either don't see the sodium. So it's more like how high is the slope compared to all the other molecular stuff.
But so it's like
the slope itself is, because you cannot.
So it's about the mutedness of the molecular features, not about.
I would say that is a better evidence for clouds because the slope. So some slopes are not lambda to the 4, and so there's steeper slopes than that. So that could potentially be evidence for clouds, but the lambda to the 4 is going to be influenced by temperature profile with height, because what you're showing is actually lambda to the 4 times gate height. And so if you have a temperature profile that actually changes, you can. So even the fact that you don't have lambda to the 4 slopes, not strong evidence for clouds for now. Plus the fact that the star is messing up. The star is changing a bit the slope. So yeah, there are crazy. HG189 has crazy big slope. There are some crazy big slope and some very slow.
Other questions? All right, if not, let's thank Vivian again and go to lunch. So I have a question. So if there's an inflated planet, you expect it to have a high entropy interior, and you expect it to not have a cold trap.
Yeah.
So are any of those Kepler planets inflated?
I haven't checked.
If they're inflated, then it's weird that'd be especially weird that they have the cold trapping.
Yeah.
You might want.
Yeah.
Might be like, oh, maybe something else happening.
Or maybe the inflation doesn't change the bit profile deep enough, shallow enough. It could place some constraints on that.
Maybe the inflation just pushes the isotherm deeper rather than making it adiabatic, which is what the turbulent mixing idea shows.
Yeah, so that, I agree. Those clouds could get actually insights of what's